Good morning, everyone. Let me share my screen. All right, so let's get it started. So we have been talking about graph theory. So we have seen what graph is, and we also have seen what is the degree of a graph, degree of a node in a graph. We also have seen some different types of graphs like directed graph, connected graph, disconnected graph, undirected graph, and so on. So today we will continue our discussion on variants of or avatars of graph, and then we will see some different concepts like subgraphs and all. Okay, so this is one of the very popular graph. This is called a bipartite graph, right? Bipartite because it has two parities. So bipartite graph is a graph in which the vertex set can be partitioned into two sets, right? Such that in these two disjoint sets, actually, two disjoint sets, such that edges only go between sets, not within them. Right? So edges are between these sets, right? So, for example, in this, what you're seeing here, we have A, B, C, D is one set, P, Q, R is another set, and their edges are always between one set to other set, not within set, right? So within sets are not are not allowed. Edges are only between sets. So this is a bipartite graph, and the example of bipartite graph, there are many real life examples. For example, let's say there are 3 jobs and there are 5 people who are appearing for the job interviews, right? So then the connection might be whoever is eligible for that particular job, we may connect them. So obviously the number, the two sets here will be the candidates, set of candidates and set of jobs, right? So set of candidates and set of jobs, and obviously you can see that the connection will be always between candidate to job. Candidates may not be connected, right? So this is called, this is an example of bipartite graph. Now question here, you have seen the definition of bipartite graph. Which among these two is a bipartite graph? Which among the above is a bipartite graph? Left one, right one, or both? Left one. Why right one is not a bipartite graph? It can be also thought of a bipartite graph actually, right? Because what it says is it has two sets and two disjoint sets such that the edges only go between sets. If I define my set to be like A and C is one set, B and D is another set, right? So between B and D, there is no edge, right? Similarly, between A and C, there is no edge, right? So if I define my set as BD and AC, right, BD and AC, then this also is a bipartite graph, which is not very obvious if you look, but if you clearly make this distinction that B and D is one set, A and C is another set, the edges are only between these two sets. Within sets, edges are not there. Right? So even both, the actual correct answer is both these graphs are actually bipartite graph. In fact, any cycle which is of length, which has even length, right? Any cycle which is of even length can be thought of a bipartite graph. Right? So you can verify that any cycle which is of even length. So here it is 1, 2, 3, and 4 length cycle. Any even length cycle can be thought of a bipartite graph. Right? So there they are. Okay. What is a complete bipartite graph? A complete bipartite graph is a bipartite graph in which each vertex in first set is joined to each vertex in the second set by exactly one edge. Right? So it's like fully connected, right? So fully connected. So question here, if I have let's say m nodes in set 1 and n nodes in set 2, right? M nodes in set 1 and n nodes in set 2. How many edges will be there total in my complete biparallel graph? Mn, correct. Right, so that is Mn. Okay, good so far. So now let's look into another graph, star graph, right? The star graph is a complete bipartite graph. Okay, so this doesn't look like a bipartite graph, but it is, because you can have this definition in which n minus 1 vertices have degree 1 and single vertex has it should be has single vertex has degree n minus 1. And so this is a typo here. This should be has. Single degree has degree vertex has degree n minus 1. For example, these are all star graph, right? So these are this, for example, if you look into this last graph, this looks like a star also, but all others are also a star graph. And here, what is the parity? Like, what are the sets? This single node will be in one set, all other nodes will be in other set. So therefore, even this graph is a bipartite graph. Only thing is, set 1 contains one edge, set 2 contains n minus 1 edges. Set 1 contains one node, set 2 contains n minus 1 nodes. Right? So this is the correction, and here also you can see that if I mark this center one in set 1 and all other node in set 2, then this is also a bipartite graph, and this is a complete bipartite graph. Okay, this is a complete bipartite graph. The single and it says that n minus 1 vertices have degree 1. So this has degree 1. This has degree 1. Right? You can see this. This also has degree 1. This also has degree 1. But this guy has degree 4. Okay? So all of these are star graphs, and I hope this is very clear. Next, weighted graph. Okay. So sometimes there is importance of weight, right? For example, if you are looking for, let's say, cities, so let's say the nodes represent cities, then these weights may be representing distance, or maybe can represent the liter amount of fuel or petrol you burn from traveling A to B. So this can be different things, but in such cases, the weights also are important. A weighted graph is a graph whose edges have been labeled with some weights or numbers, right? So A and B is labeled with 5. This is called a weighted graph. A multi-graph, okay? A multi-graph is not a regular graph. It's not a simple graph. A graph in which there are multiple edges between any pair of vertices. Between any pair of vertices, there are multiple edges. For example, between B and C, there are 2 edges. This is something like you have, let's say, two cities, Jodhpur and Jaipur. There are 2 roads, right? If there are 2 roads, maybe I would like to show that as 2 different edges. Yeah? So there are edges from a vertex to itself, right? So either it has a multiple edges or it has a self loop. Then this is called a multi-graph. Another interesting thing is a planar graph, right? So what is a planar graph? A planar graph is a graph that you can draw in a plane. So that you can draw in your paper pen, right? So your paper in such a way that no two edges of it cross each other except at a vertex to which they are incident. Right? So they should not cross, the edges should not cross each other. And if you can draw any graph in such a way, that graph is called a planar graph. Right? So if you look into this, very clearly you can say the middle one is definitely a planar graph. Why? Because none of the edges are crossing each other, and you can draw this in your paper, right? Without in your paper, you can draw this, and none of the edges are crossing each other. This one, the last one, is also a planar graph, obviously a planar graph, because none of the edges are crossing each other. Question, is this the first one? Is the first one is a planar graph? Yes, no. There are some yes, some no, but it is yes because, of course, in this drawing it is crossing, but I can always draw it in a different way, right? I can always draw this graph in a different way so that it becomes planar. Because, for example, I can draw this uh, like this. No, I can this edge, right? So this edge which is here, I can draw this outside. The graph remains same, right? If I, instead of drawing inside this edge, I can draw it outside, right? So this edge, if you see that the diagonal one of the diagonal one, instead of drawing it inside, if I draw it outside, then I am done, right? So then none of the edges are crossing, and even this is planar. So you can, when the question is you can draw or not, but it's not always possible, right? So it's in these three examples we have seen that all of them we can draw in the paper without crossing the edges, but it's not always possible. We will see example. So this is what I was telling, right? So this graph and these two graphs are equivalent, and you can always draw it like this. But then there are some graphs which are non-planar graphs, right? You can actually not draw. And there are some formulas to it, like you can actually identify based on that formula, but we will discuss that later. But at least now, graph that is not a planar graph, right? It's called a non-planar graph. In other words, a graph that cannot be drawn, right? So you cannot draw, that cannot be drawn without at least one pair of its crossing edges is non-planar graph. For example, this graph, you may take your paper pen and try drawing this without crossing. So what you will do, maybe you will put one of them outside and this one also maybe outside, but you will end up having some configuration so that it crosses each other. You will never able to find any any drawing which does not cross the edges, right? So you will always have a problem. So we can try this as an exercise. You can just play with it, drawing it different way, but you will always fail, and you will always have at least one crossing. So therefore, this graph is a non-planar graph. That means you cannot draw it in a plane without crossing edges. All right. Okay. One more graph. We are looking into multiple avatars of the graph, right? So it's good to know these concepts because they might be useful here and there, right? So we'll just use them. Okay, so this is called a multi-relational graph, right? So multi-relational graph is a graph in which each edge denote one of the relation from a set of relationships, right? So or a set of relations. It is called a multi-relational graph. For example, this graph, I hope you might have already noticed whom I am talking about, but this graph is a knowledge graph, right? And the knowledge graph has some QID associated with people, right? So this is a QID associated with a person, and is an instance of, is a label of this is human. His occupation is cricketer, and Anushka Sharma is his spouse, and I am sure you might have guessed who he is, and he has an image this, right? So Virat Kohli. So this type of graphs are like there are edges which have some labels, right? It has an image like this, and these are labels. Right. So you can have more edges like he is born in India and he is citizen of India and so on. So this is like this is multi-relational graph. Okay, so 20th, of course, it doesn't end. Maybe there are more versions and more parts of graph, but at least important ones we have covered. The 20th one is called a tree, right? So this is another thing. A tree is a graph, right? Tree is a graph in which any two vertices are connected by exactly one path. Okay, so any two vertices are connected by exactly one path. So if you take any two vertices, right, you can have only one possible path. Here example, I took this two node, there is only one path. Any two node you take, there is only one, exactly one path. But if there is more than one path, that is not a tree, right? So if I connect this, right, if they connect these two nodes, right, then it will not be a tree, because then you will have two paths between two of the nodes. So this definition also says that you cannot have cycle in the tree, right? And if you do not have a cycle, and that's a graph, if it's a graph which does not have a cycle, then it's a tree, right? As soon as you have a cycle, it does not, it violates the definition, and it is no more a tree. So tree is like a widely used data structure also. Like I think you guys are doing data structure, right? Are you doing this semester? Yes, no? Or you have already done? You did last semester. Okay. So you did last semester, so you already know the tree. So there are numerous applications, and but this is more of a mathematical course, so we are not dealing with that. But I hope like there are different versions of trees, like binary tree and binary search tree and all. But essentially, this is the definition which is quite correct, right? So you can. All right, so we have done some part of the discussion today. Now let's do a quick round of a quiz, right? So let me present it with Slido so that you can join. So you can join now in the slido.com G418, right? G418. There are some true false questions. So let's do this. T3. All right, so now we have 20 seconds to answer. Multi-relational graph can never be a multi-graph, true or false? Multi-relational graph, the Virat Kohli example, right? You remember, cannot be a multi-graph. True, false. The answer is false. And why it is false? Because you can have a multi-graph, right? So, for example, Virat Kohli is citizen of India, and Virat Kohli born in India. Right? So you can have two ages between Virat Kohli and India. So it's definitely it can be a multi-graph. Okay. Good. So let's look into next. A tree In a tree, a node cannot have more than degree 2. In a tree, node cannot have more than degree 2. Oh, this is surprising. A tree, a node cannot have more than degree 2. It can have more than degree 2, right? tree can have more than degree 2. So it's not just a binary tree we are talking. The tree can be ternary or anything, right? So we can have any node. The only, if you remember the definition of tree, is only thing it says is there is no path, no, there is exactly one path between two nodes, right? Exactly one unique path. So even if I have a node and then this node has, let's say, 10 children, right? Then the degree of the first node is 10, right? Degree of the root node, like if again I'm talking in the data structure terminology, if you have a root node and then the root node has 10 children, right? So the root node has 10 children, that means the degree of root node is 10. All other nodes have degree 1, so degree can be more than 2. It doesn't mean, it doesn't have to be less than 2 or something, or exactly 2, anything, right? So it can be more than 2. False is the answer, and this is very surprising to me. Anyway, but at least few guys did correct. The star graph will become disconnected if we remove any one node. Any one node. If you remove any one node, it will become disconnected. Any node, let's call it any node if you remove, right? What is happening? Maybe interpretation is wrong, but actually if you remove any node, if you just remove the center node, then it will become disconnected, right? I hope that's what you mean. But the question was like, if you remove any node, it's not like you remove any node, then it will be disconnected. If I remove the outer node, it will not be, right? So I don't know why is that. Anyway. Okay, last question. Yes, this would have slightly more time, I guess. Yeah. Okay, so maybe the time is less. I think that's why you are making this type of mistakes. Okay, so I think we need to revisit these questions. But the answer is false. It's not a fully connected. It's not a complete bibrated graph. And why is that? Let's maybe at least quickly look into this. I think it's a bit of a surprise. Is it because of time you guys are struggling? Or you are really sleeping in the class? Just a minute. So what is it saying? We have, so let me share the screen. Okay, I hope you can see it. Yeah. So the question was, you have a set A, right? So A is set of instructors. Right? Let's call it I1, I2, M instructors. And if we have set of instructors, and then B is the set of courses, right? B is the set of courses, C1, C2, and Cn. Right, so there are n courses in the IIT Jodhpur, and then there are m instructors, right? So a set of instructors, and if we connect element of A and B by the relationship instructor teaching a course, right? So when an instructor is teaching a course, you will be connecting them. If they are not teaching, you will not connecting. So I1, I2, and IM, C plus C1, C2, and Cn, and the connection is, if let's say I1 teaches C2, I2 teaches C1, IM teaches CN, and so on. So will it be a fully connected graph in a natural setting? When
No, sir.
sorry?
Every instructor will not be teaching every course.
Yes, every instructor will not be teaching every course. I'm just teaching M4C this time, right? So let's say this is M4C and this is Anand. I'm just teaching M4C. I'm not teaching any other course. So it's not a fully connected graph. Therefore, these connections will not be there, right? So this type of connections will not be there. So this is not a fully connected graph. So just a minute. Uh, uh, okay. And it will become a complete binary. It's not, right? Okay. Anyway, so you're done with this small quiz. Now, okay, let's not do this. I think we can. Fine. So this is like you should have understanding of now this definitions. I think I strongly recommend you guys to look into these slides once again and understand the definitions properly after the class, right? There was some comment in the chat box. Let me see that. Mm. Even binary tree have degree 3, yeah. So even binary tree can have degree 3, right? So binary tree can have degree 3 because let's say the parent, if you also count the parent, right? So parent is 1 and then 2 child. So it can have degree 3. Okay. All right, so now let's look into some more definitions, right? So this is more of a definitions. These definitions are very interesting and you should have a proper understanding of that. So a subgraph, what is a subgraph? So we have seen subsets. So similarly, there is a subgraph. A subgraph of a graph G is a graph, right? So it should also be a graph H such that V of H is subset of V of G. The vertices are subset. Edges are also subset, right? Vertices are subset as well as edges. And we say that H is a subset of G, graph G, H is a subgraph of G, and G contains H. This is how we read it. Right? So this is, for example, this is a graph G, and the one H is a subset of this, right? Because all the vertices are there and some edges are removed. It's also possible that you remove some of the vertices. Even then, this will be a subgraph. Okay. Another definition, independent set and clique. What is an independent set or a stable set, some type people call? A set of pairwise non-adjacent vertices. A set of pairwise non-adjacent vertices. For example, in this graph, right? So you have this graph. U and V are not independent set. Why they are not independent? Because they are connected, directly connected. U and W is also not independent. But U and X is also not independent. But U and W, right? U and W is independent set. Similarly, Y and P is independent, right? Similarly, X and V is also independent, right? So you can find multiple independent sets of size 2. Can you find an independent set of size 3 in this graph? Can you find independent set of size 3? So what is independent set? Clear, right? So UW is an independent set because they are not connected. YP is an independent set. XV is also independent set. But X and U is not an independent set because they are connected. So the question is, can you find a independent set VXY VXY, but XY is not independent. YPW, YPW, but B and W are connected, right? No, yeah. So if you are giving an example, let's say YPW, but PW are connected, so that's not an independent set. So independent set, all the elements should not be connected to each other. No one. Yeah. So you cannot find an independent set of size more than 2 in this graph. All right. So all the nodes, all the elements should be not directly connected with each other in the independent set. A clique is just a reverse concept. A set of pairwise adjacent vertices, right? So these are like a clique contains elements and then those elements are connected to each other. For example, U, V and X, right? This is a clique of size 3 because U is connected to Y is connected to X and everything is connected to each other. So UXY is a like clique of size 3, but BW is a clique of size 2. UV is clique of size 2. XW is clique of size 2, but XWP is not a clique, right? XWP is not a clique because they are not connected to each other. So you cannot find more than 3 size clique in this graph. Am I correct? You cannot find clique of more than size 3 in this particular graph. Right? But let's say I have a fully connected graph, right? Fully connected graph of 2, 3, 4, 5. Let's say 1, 2, 3, 4, 5 nodes. Fully connected graph of 5 nodes. What will be the click size? 5. Yeah. What will be the click size? 5. And will there be any independent set? No. The independent sets, there will be no independent set, but there will be a click size of 5 in that case, if it is a fully connected graph. All right. Good. There is another interesting thing, chromatic number. So what is a chromatic number? Chromatic number is also called graph coloring number, right? Graph coloring number. It is denoted as Ji of graph G is the minimum number of colors needed to label the vertices so that the adjacent vertices receive different color, right? Minimum number of colors needed to label the vertices so that the adjacent vertices receive different color. Consider this example of map coloring, right? So you have a map of India and then there are different states. So you obviously want to color different states in a different color, but in such a way that the neighboring states have different color, right? Neighboring states should have different color. So obviously, so there are 30 states in India, you don't need 30 colors, right? Because you don't every state is not adjacent of to everyone. For example, if you remember the map of India, Rajasthan now, right? So Rajasthan is neighbor of what? Haryana, Gujarat, Madhya Pradesh, I guess. So if you Haryana, let's say Rajasthan, if you are coloring with red, Gujarat, you will be coloring with green, maybe Madhya Pradesh, something else, and so on, right? So you should not be, the neighbors should be of different color. That's the notion. So is the minimum number of colors needed to label the vertices so that the adjacent vertices receive different color. For example, in the left hand side, how many colors do I need to satisfy this? Yeah, so it is saying minimum number of colors, right? Maximum number of colors will be obviously number of nodes, right? Number of nodes, because if you color everything differently, but this is minimum number to satisfy this condition. Now, question: this left-hand side graph, right, which has 4 nodes. What is the minimum number of color I need? 2, right? How do I do this? I can make it red and green, red and green, right? Red and green. This 2 color will be sufficient red and green, because they are not, because red and red are not connected, green and green are not connected, and I'm done. So two colors, but you can you do it with one color? No, because if you cannot do it with one color, because if you use red color, the adjacent node has to be different color, so you cannot do this with one color. So the chromatic number of this left graph is what? What, 2 is 2. Now this one, there's a good exercise, no? Okay, so this I'm leaving you to this 4. If you want color, let's say this and this same, this same, this same, this same. This one, if I use red for all of them, there is no problem, right? Then, but if I use red for this, I have to use green for this. But if I use green for this, I cannot use, so I have to use yellow for this. And if I use yellow for this, I can still use green for this. Can it be done in 3? Anyone? 3 is surely minimum, but can it, can it be done with 3, or it needs 4? Probably. Okay. So yeah, let's think. I think it is 4, but I am not confirming it. So you can check it. Okay. You can check it. So this graph, you can check it. Okay. We can talk it later. Right. So now, complement of a graph. Another definition. Another simple concept. Complement of a graph is denoted as G bar of a simple graph. G is a simple graph again, with vertex VZ denoted by UP is the subset of EG, right? So if and only if UP is not an edge. I mean to say, what is a complement graph is very simple, right? So if you have a graph given, you remove all the, you make it fully connected first. Okay, no, let's not make fully connected. You remove all the edges which are not there, and you add all the edges. Sorry, you remove all the edges which are there and add all the edges which are not there, right? So for example, this one, right? So UV is there, I will remove UV. PW is there, PW I will remove. WX is there, I remove. XU is there, remove. This, remove. And then you will find this edge, all others which will be connected. Right? So union of these two graphs, G bar, G and G bar, is a fully connected graph, right? The union of G and G bar is a fully connected graph. Though we have not defined the union, but you can understand from the concept of set theory. Union of G and G bar is a fully connected graph. And you can definitely also think about the independent set and click. They will also change in some way, right? So we should pay attention to that also. Okay. So this is called complement of a graph. Okay. Now, how do you represent graph? So you might have already seen this as well in the courses. So this is more of a mathematical way to represent, and adjacency matrix is one of them. Of a graph, G is denoted by AG, right? A of G, adjacency matrix of graph G is, what is the size of this graph? Is the number of nodes into number of nodes, your number of vertices into number of vertices, size square matrix, whose ijth element denote number of edges between ith and gth vertices. So it can be depends on things like, if it is a weighted graph, it denotes the weight, or it can depends number of edges between them. So it depends on how you are trying to represent. So this is a graph. Huh? This graph has how many nodes? W, X, Y, and G. 4 nodes. So the adjacency matrix will be 4 cross 4. Right? Adjacency matrix is 4 cross 4. And W is definitely not connected with W. So 0. W is connected with X with one edge. So 1. Right? W is connected with Y with one edge again 1. W is not connected with G, so 0. Similarly, X is connected with W 1. X is not connected with X itself. There is no self loop, so 0. X is connected to Y, but it has two edges, right? C and D. So therefore it is 2. X is not connected to G, so therefore it is 0. So you can find it, but you can also represent these things in a different way, like you can also put the weights and so on, right? So this is a way to represent adjacency matrix. Now you can think of what are the advantages and disadvantages of adjacency matrix. It is like a storage wise your sparse matrix, but you are taking a lot of space, right? You are thinking that. Incident matrix. Incident matrix is another way to represent this, but this incident matrix, the size is number of vertices into number of edges, right? The size matrix ijth element is 1 if the vertex is an endpoint of that. Ith vertex is the endpoint of jth edge, right? For example, this particular graph, what will be the size of incident matrix? Anyone? What will be the size of incident matrix in this example? It will be number of vertices into number of edges, right? So 1, 2, 3, 4, 4 into 1, 2, 3, 4, 5, 4 into 5, right? And that's all it is. So W, X, Y, G, A, B, C, D, E, right? So these are the edges. And whether W and A are incident, W, A is incident or W or not, you denote it in that like that way. Right? So this is called an incident matrix. Third way of representing is called a linked list of neighbors, right? So you can have a multiple linked lists for each of these nodes. You have a linked list. A, what are the neighbors of A? A's neighbor is B, C, and D. B, C, and D is neighbor of A. B has only one neighbor, A. C has two neighbors, A and D. C has two neighbors, A and D. And D has two neighbors A and C. D has two neighbors A and C. So you can also represent as multiple linked lists. Okay. Okay, so this is perhaps the last concept for today, mostly. So this is what is an isomorphism? An isomorphism from a simple graph G to a simple graph H is a bijection, right? Bijection means 1, 1, 1, 2. Is a function f g bg to bh, right? So it's like two graphs are called isomorphic if they have one-to-one correspondence between their vertices. Right? For example, these two graphs, they look very different. They look very different if you look, if you see, but they are isomorphic. Why they are isomorphic? Because you can find one-to-one correspondence between them. Like W is C, X, B, Y, D, and G, A, right? W is correspondent to C, X is correspondent to B, Y is for D, and G for A. So these two graphs, though like at a glance when you look, they look very dissimilar, but they are isomorphic to each other. This is just a concept to know. Okay. This is a very important slide. You should definitely know this because sometime in this course or anywhere when we discuss things, we might be just discussing in these notations. We might be using these notations. So P of n is the path of size n. C of n is cycle with n vertices. N of n is a null graph. K of n is a complete graph with n vertices. K of Mn is a bipartite graph between two independent sets is called Kmn of size M and N, right? So the two sets in the bipartite graph, they are of size M or M and N. Okay, so this is this notations you should definitely remember because they will be just used. Okay, now let's look into last thing for today, which is again some quiz. So I hope so you have to join the same G418. So please join and you can answer now. What will be the chromatic number for an empty graph with n vertices? Empty graph with n vertices. Empty graph with n vertices. Oh God. Okay. So one is correct because it's if it is an empty graph with n vertices means there are n vertices, but empty graph means there is no edge, right? So if you remember the definition of empty graph or null graph, that is the graph which has vertices but no edge. So if there are vertices but no edge, you can use just one color because they are not connected to each other. So their chromatic number will be 1, right? They're not connected to each other. So even if you use the same color for all of them, it's fine, right? If you use same color for all of them, it's fine. So therefore, the chromatic number is 1. Good. Chromatic number of a bipartite graph is always equal to chromatic number of a bipartite graph is always equal to. Okay, so at least this time 86% are correct, but 14% are still making a mistake. So if you remember the bipartite graph, right? So it has two sets, and each of these sets are there are connections only between sets. Within sets, there are no connection. So if there are connections between sets, one set you can color in red, the other set you can color in green and you are done because that's how it is, right? So you just need two colors and you actually need two colors. One color you cannot, right? Okay. Last, complement of a star graph is always complement of a star graph. Remember your star graph, right? But it's not correct. Means in general, okay. So this is maybe slightly controversial, but yeah, let's see. What do you respond? Yeah, means in general, am I audible? Just a minute, there seems to be some connection issue. Am I audible? Hello? Yes. Okay,
Yes.
thanks. Thanks. So just a minute. Yeah, so this is like there might be boundary cases where this may not be true, like boundary case in the sense, let's say a star graph of 2 node, right? This may not be true for that. For a star graph of 3 nodes also, you trace just this, if you remove, yeah, it may not be true. But this is true, like this question is slightly that way controversial in some senses.
Sir, but
But
the central vertex will not be connected to anyone. So how can it be a cyclic graph?
sorry, yeah, so for 1 and 3, it will not be. That's what this question is wrong. That's what I'm coming to know. So if you have a node or just one node, sorry, 2 nodes star graph, 2 node star graph, it will not be cyclic, right? If it is a 3 node star graph, it will not be cyclic as well, right? Because you have just 3 nodes. So you will have just one connection. But if you have 4 nodes cyclic graph, what will happen? 1, 2, 3, and then you will have a cyclic graph, right? So
Sir, but
beyond, Yeah.
Central vertex will not be connected. So how can it be cyclic? For cyclic, we need a single cycle that goes around in the whole graph.
Not really. Cyclic graph is a graph which contains a cycle, right? A cyclic graph is a graph which contains a cycle. So that's a definition, right? So it's not like it's all nodes should be connected and all. Even if some nodes are connected or not, but if it contains a cycle, that's a cycle graph. But yeah, this question is like only true for nodes greater than 3, right? But that's I think more or less. Is that clear? So maybe what's the time? Just a minute. Okay, we can still discuss quickly, just a minute, so that this question is clear, because you can see my screen. Yes. So what you are saying is cyclic graph. Right? This is a star graph, right? So if the complement of this will be connected, this will be connected, this will be connected, and all other edges will be removed. Be removed. This will be removed. This will be removed. Right? So this does contain a cycle. So this is a cyclic graph, right? It is, but if so, the another thing is, like, if you have is this a cycle? Is this a star graph? This is also a star graph, right? Because this is just a 2 node and it says whatever is a star graph. Even this is a star graph. But in these cases, there is no cycle forming, at least here, right? So here you have only 1 node. Yeah. For these 2 cases, there is no cycle forming in the complement of this. But beyond that, you will always have a cycle. None of the Yes, none of them will be correct always. In general, if it is, that's a correct answer. Yeah, if you consider all the cases. Yes. Okay, so strongly recommend. Can't it be empty graph? Uh, Empty graph. So you said 1 node, like, or no node. So 1 node. This is, yeah, by trivial definition, it is. It can be anything, right? So it can be star graph as well. Nothing, no violation of the star graph definition. So even this is a star graph, this is a star graph, this is a star graph. Okay, so strongly recommend you guys to look into the definitions, understand them thoroughly, because otherwise you will make mistakes. So whatever covered in last 2 lectures, we will discuss few more things, especially around graph coloring, Eulerian path, Hamiltonian path in this lecture, this course. So a couple of more lectures on graph theory, and so that will be, today is what, Tuesday. So yeah, we will meet again on Thursday, and Friday is holiday again. So Thursday and Saturday we will complete this graph theory part, and yeah, that's all. So please have a look into all the definitions which are covered in the course so far. And if you have any doubt, you can ask it in the next lecture as well. Okay. All right. Thanks for appearing in the class. Bye.